So, welcome everyone. Thank you for joining me today. I hope you've been enjoying your lunch as much as I did. I know it's kind of a topic like it's lazy after lunch. It's kind of not a good match, but you're going to be really interested with this one. You're going to be having fun, and I hope that you take something out of the presentation. So, well, we're going to be talking about laziness. So basically focus on lazy evaluation and how to unleash the power of generators in the Python context, uh, aiming for some more efficient and elegant type of computer and performance in our web applications, scripts, and programs on Python. So let me introduce myself. I'm Sebastian Arias. I'm a software engineer from Ecuador. So I've been traveling a lot to get to the conference, like around 10, 12 hours. So in my experience during this time that I've been coding in Python, I've have seen from firsthand how lazy evaluation can help us to optimize our applications with some simple steps leveraging from generators. So let's get started like checking these two topics, lazy evaluation and eager or static evaluation. I know that you might have heard about this in the past or maybe something is ringing about right now, but let's check some context about this concept. So lazy evaluation is a programming technique where expressions are evaluated only when the results are needed. So they are aimed for improving efficiency and avoiding unnecessary calculation. So in other words, it's a technique where we delay the evaluation of expression until the result is actually needed. So this can be extremely useful when we are dealing with a lot of data, like large data sets, data streams, and this kind of situations that we can encounter. So this basically reduces the unnecessary computations when we are evaluating something. So what's the difference with static evaluation or eager evaluation? So the key difference between lazy evaluation and eager evaluation is that eager evaluation evaluates the expressions immediately upon binding with a variable. So right when we start using the variable there, we are going to be doing the calculations of what we are expecting as a result. On the other hand, lazy evaluation delays these calculations until we really need the result. While lazy evaluation handles this type of information that way, it unlocks some features that we can have, for example, infinite data structures or infinite type of elements that we can generate. Something that definitely we can do with eager evaluation because we will run out of memory. So, why or when to use lazy evaluation? So basically, this is useful when we want to avoid unnecessary work or handle potential infinite databases. So when computation happens in lazy evaluation, it unfolds it step by step, saving performance and memory. So this can be found on different type of scenarios. Some that I write down is like dealing with infinite data structures. That's something that I'm going to repeat a lot during the session. Like streams, infinite number sequence, and avoid these necessary computations and performance issues. Also, optimizing performance is like delaying the calculations for when the results are needed and then cache them. And also avoiding some type of errors, maybe with conditional logics and everything, because we're handling that logic in just one place. So, how lazy evaluation looks like? I come from a Haskell background that is a functional programming language that has this concept of lazy evaluation built-in. So here's a typical example of Haskell. Like this is a lazy sum or a function that is going to be adding elements from a list. So as you can see there, the lazy evaluation differs the computation step by step. So in this example, lazy evaluation, we have lazy sum that has the base case, like lazy sum with an empty array, it's going to be evaluated as 0, right? Because we don't have elements to adapt, so it's going to be 0. So in the second block, you will see that lazy sum has a parameter 1, 2, 3 that is a list basically, and we are kind of going step by step incrementally doing this evaluation. So first of all, we are taking the first element that is 1, and then we're going to be adding up the rest of the list, right? So we're going to be doing the lazy sum of 2 and 3. afterwards, we're going to have already number 1 plus number 2, that is the next element that we have on lazy sum, and call that function again just with the parameter number 3 on the list. And finally, we're going to the base scenario like lazy sum with an empty array, but we already have all these values unfold, right? And at the end of the day, we reach the base example like lazy sum of an empty list is equal 0, and that's going to be the lazy evaluation that we are going to have there. As you can see, we're in kind of ensuring efficiency in terms of performance and the memory usage, because we're waiting until the result is needed to do the calculation of the expression that we have there. But how lazy evaluation works in Python, and how can we do it in Python? So in Python, lazy evaluation can be done in using the iter function and also the next function, right? That might ring a bell with iterators. So basically, when we produce iterators, we are using lazy evaluation because under the hood, they are grabbing up the expressions into a lazy expression or lazy values that we are going to be yielding through time when we call this type of iterators. This basically ends up being a generator, right? So lazy evaluation in Python is achieved by using generators and the yield keyword, as you can see there, right? So here we have a basic example of a generator that is going to be a lazy sequence, I call it there. As you can see, it's infinite because we have an infinite loop, like while through. So if you can imagine this with a return statement, it will break, right? It's going to return I, and that's it. Here, the yield keyword is going to stop the iteration right there and the calculation, and remember in what part of the function the execution was paused for subsequent calls. So in this scenario, when we use next sequence, we are generating the value on the fly, so it's going to be calculating it every time that we are calling it. Instead of grabbing all the sequence in memory, it's going to be producing it on the fly. So, well, now wrapping up, so what are generators as a summary? So basically, they are a special type of iterator that produce a sequence of values on demand using the yield keyword. Unlike lists and tuples, this generates values on the fly and doesn't store anything in memory for this unlocks efficiency at the time of larger datasets or data streams. We've seen a little example, but how we really define a generator, right? So we've talked about the yield keyword. So basically, we're going to be creating a generator, something like similar like a function, right? As you can see, we have the def keyword, that is basically the initialization of the function. And instead of using the return keyword, we're going to be using the yield keyword. So this is the main difference that creates a function and a generator, right? So a generator basically has a yield keyword. In this example, it's kind of some verbose implementation for making it kind of more visible of how it works. It's a custom range functionality, like the range function that we normally have built in on Python. But this time, as you can see, the main difference is that we are yielding the value, and afterwards, we are kind of calculating the subsequent value when the time comes in the next call, right? So one thing that I want you to notice is line 12 and 13. So you see that I have in line number 10 a variable called myRange that it's being assigned or binded to my custom range with some parameters set up, right? So when we ask Python what is the type of myRange variable, as you can see, it's a class generator. So Python already identifies this as a generator class, right? But what if we check the type of my custom range? As you can see there, my custom range is a function, right? Also, you can see that we are returning a generator in the time hints. So it's kind of a built-in functionality that we can leverage from using Python on daily basis. And on line 15 and 16, you can see I'm using it just on an iterator, right? I'm using the next function, and it's going to be generating the values on the fly. So let's focus now on the generators usage, right? So I have two examples based on the custom range that I have. So lazy iterators basically can be used as iterators. So they can be used as normal iterators using loops, using the next function, anything that can happen with an iterator can happen with a generator. So basically, as you can see here, we're using the the for loop for getting all the elements of my range custom variable that is assigned to the generator that I previously showed you, and it's going to be printing all the elements from that generator, right? So instead of allocating that in memory, it's going to be produced every subsequent call. And also, we can use the next function as I previously mentioned. Also, you may like, or one of the things that I most like from Python is the comprehension, right? We have list comprehensions, one-liners that are really powerful. We can add conditionals, we can add anything there. We can do the same with generator, right? But instead of using the square brackets, the syntax changes a little bit using just parentheses. As you can see on line number 2, I have that function that is multiplying by 2 all the elements in a range, and it's going to be yielding the values on the fly, right? So once again, in line number 3, I'm checking the value. So it's being a class generator in a one-liner. You don't have to define a function if it's not needed. So if your logic for that generator can be handled in one line, you can do it that way. And also, it's kind of feel more familiar, right? It's kind of a traditional comprehension that we have right there. So you can start looping it using the next function, using loops, etc. So that's basically a comprehension generator. So we've talked about how generators unlock lazy evaluation in Python, right? All the performance, all the memory, but let's stick to something more tangible, right? So let's do some benchmarks that I've done previously, because it would take a lot of time in a live scenario like we have here in the conference. So let's focus on memory efficiency right here, right? So here, as you can see, I'm using a memory profiler to check how the memory is being changing, or is incrementing or decreasing in terms of execution, right? So I have a generator, a data generator, that basically is generating numbers from 0 to 1 million and yielding them to be looped in a function that it's going to check if every item is even or not. So in this case, as you can see, when we start execution, we have 21 megabytes being used, and when we start looping, nothing happens, right? We are not using extra data. So we are kind of not allocating nothing in memory. It's just generating values on the fly and make them available for us to use in a loop. The execution time, it took like 20 seconds, 21 seconds if you round up, but that's the thing here. But what happened with eager evaluation, right? In eager evaluation, we have basically the same. Here it's a little bit verbose. I know that this code can be refactored and be more fancy right here, but I want to make it as visible as possible for you to have an idea of what's happening in fact. So here we're using a list comprehension, as you can see here. We're using range, that is a built-in generator for generating the 1 million values. We're having this allocated in memory using a list that is going to be set up in memory, right? And then we are looping this in a for loop to check the items. That's why we have 2 million occurrences instead of 1 million occurrences, right? But the thing is that look at the memory increment. 9 megabytes, right? In the previous example with the list evaluation, we have 0, now we have 9 megabytes. So that's the increment. But you might say, like, it's 9 megabytes. Who doesn't have 9 megabytes available, right? But imagine this with a list of 1 million numbers. What happens if we have more information, more data to process? It's going to be escalating, right? So that's kind of the difference right here. I'm not sure why the execution time is not showing here. Oops. Okay. Well, let's jump into the results. So basically, we're losing 3 times less memory, from 0 to 9 megabytes, comparing lazy and eager evaluation, and it's 1.5 times faster in execution. I'm not sure why it's... no, there we go. So this took about 29 seconds to execute the same logic, right? So these are the results for memory efficiency. So let's jump to performance optimization. So now I've refactored a little bit the code. Inside that generator, I've already added the logic for the checking if it's even or if not. So basically, the generator, the range, is going to be creating values from 0 to 1 million, and I have a conditional, like if it's even, it's going to yield it, or not, it's going to pass to the next one, right? So in this example, what you can see is that the occurrences are even less, right? Because it just happened one time. It's kind of calling that as an iterator. The iterator is not using memory. Everything is being on the fly. And we're going to be returning the addition of all of them. So as you can see, there is no memory increment. There is nothing that has changed in our system. And the execution time is less than a second for 1 million elements to be added up in the process, right? But what happens with the evaluation? Now we have a fancier list comprehension there. As you can see, we have now added the conditional, so it's checking if it's even or not, and it's storing it in a list. So as you can see, now the memory has increased to the double as we used to have prior, right? So now we are using 10 megabytes due to the processing and everything, but that's allocated in memory. So that's something that at time of performance or maybe memory efficient, let's say that we are doing something really, really particularly that we need to make it as efficient as possible and not consuming resources, you know, that can be some tricky part of things. Okay, let me get back. There we go. And the execution time, as you can see, is been increased like in 10 seconds. So we have less than a second versus 10 seconds almost in execution time for the same logic. So we have used 2 times less memory for this example, and also it's been 17 times faster. So I don't know, it's kind of good to have that, right? So generators advantages. As you can see, there are a lot of in terms of memory and performance. So generators have several advantages. They are more memory efficient. They are lazy evaluated. They generate values on the fly. They can handle infinite sequences. So you see that it manages 1 million items like nothing. So it's efficient in that way. And also this makes a great tool for working with large data sets or streams of data. So some other applications of generators in terms of examples that I came through that I've checked on daily basis. So one of them is processing large data sets. For example, we all have worked with CSVs, right? We have different number of rows and everything. I created a CSV file that has 1 million records. It has a lot of columns, a lot of information here and there. So in this term, I created also a read CSV with generator that basically is opening the file, and instead of storing that rows internally, for example, in a list or something like that, is yielding the rows. So as you can see, is reading the file, it's looping through that file 1 million times, and then I decided not to add any logic. It was not necessary for the example. You can see that the increment of memory is slightly different than the other scenarios. It's just 0.1 megabytes in terms of opening the file, you know, loading something in that regard. But the thing that came really exciteful for using lazy evaluation is the execution time. It took less than a second to have the file open and loop into all this information that we are doing. In this example, I think that it's not kind of a quite performant way of doing this because there are other tools like pandas, polars, and other type of things that read CSVs in a more optimal way. But just to make it an example here that with this type of tooling, what happens, right? So here I have the file being open, the file being read, and I'm storing each of the rows in a list in memory, right? Look at the increment that we have in line number 10, right? We have like 800 megabytes. So imagine what would happen if instead of having 1 million lines, it's 10 million lines or something like that. So you're going to extrapolate, and at the point we're going to be running out of memory, even if we have kind of a huge server to process this type of information. And also, look at the execution time. It's almost 10 seconds compared to what we have with lazy generator. So what are the results? Basically, 38 times less memory used in the process, right? Since we are yielding values, we are just using that. We are not storing anything locally in memory. And also, it took less than a second to read the CSV file completely. For infinite sequences, this is kind of a tricky example to have, specifically when we are kind of focusing and comparing it with data structures like lists or tuples or something like that. Because if we have infinite number of items, we would need infinite memory to allocate them, right? So it's kind of complex to achieve. So in this scenario, as I put a note there, it's kind of impossible to have this example here on local because we're going to be running into a memory error, right? We run out of memory, we overflow our memory, the computer is going to be crashed. I didn't even try it because I know that it was going to mess up the, the computer, so I didn't even try it there, but that's something that it's a limitation that we might want to avoid, right? So here I came through this example. It's kind of a simulator of a temperature sensor for some example there. As you can see, once again, we have a while true loop that it's an infinite loop. So we have an infinite sequence that is going to be yielding temperature as much as we call that iterator. Another thing that comes to my mind when I think on infinite structures, I love stocks. So, you know, the prices change every second, right? So that information can be a data stream that we can handle this way. So, to sum up and to give you some takeaways in my experience of using lazy evaluation, generators, and this kind of concepts. So generators are a powerful tool for improving the memory and time efficiency of our Python programs, applications, scripts, depending on where we're using it and how we are using it, right? So by embracing lazy evaluation, we can build more efficient and scalable applications through time that can avoid these kind of limitations in terms of memory and time performance, evaluation processing, etc. So that's what I wanted to share with you today. So thank you very much. I hope you find this useful, interesting. You take something home to try, and I'm happy to have to take any questions that you may have from your end. So thank you very much for your attention.
Okay. Thank you, Sebastian. Do I have a microphone? Okay, thank you, Sebastian, for your lazy suggestions. Do we have questions? We have one up there. Here I go. Hang on. Do something, Sebastian. I need time. Go.
Hey, thanks for your talk. I essentially just need help to understand the slide. If you could go back to the first slide you showed on memory usage. I just couldn't understand the numbers because it felt like the results
on the example, right?
Yeah, the first one you showed. I think the results were even more drastic than what you claimed. Or
this one right here?
Let me... Yes. So what I'm reading there is that the 21 megabytes were used by the memory profiler, not by your fund, right?
Correctly, yeah. The increment that we have on line number 5 or 14 that you see at the start of the memory profiler is mounting the script and doing other stuff.
All right, so the usage of your data generator, that's essentially negligible, right?
Exactly, it's basically here.
Okay, so then can you scroll down? So now I have two things I don't understand. How come the increment is only 9, but then the memory usage jumps by 46 megabytes?
Yeah, that's a great question. So as you can see here, basically the increment is talking about what we are using to store the information. The 64 might be some other background stuff that is happening during this processing.
All right, so then, comparing 0 to 9, that's essentially infinitely more.
That's right.
Right, but then so then you only say it's like 3 times less, so I was confused in the next slide.
Okay, yeah, well,
like
I compared 0 with 9, it's kind of, well, yeah, I think that I did the math wrong there. That's a great catch for me to improve in the presentation. Thank you for noticing.
Okay, excellent, thank you.
Okay, anyone else? Hands in the air. Oh, okay, here I go. So.
Thank you for slides. I also like generators in my life, like Rodrigo too. And a small suggestion: you compare on your examples to generate data and provide this data. Have you compare, for example, create a list previously and access data from this list and return data and measure only this and compare this to access the next element in generator and return the next element from generator, because the clear compartments is not to create data and after that access every element. You should compare in this case how you access the one element in a row, generated row or existed row, and return it. And in this case, of course, lists is always faster because you don't need to have the context switching.
Yeah,
Have you compared it?
I haven't compared in that specific scenario, but that's one thing that we have to take into account. Generators, one kind of pitfall, let's say, that they have is that you can access data that it's already generated. It's just a one time. So if you need, in the use case, you need to allocating memory because you are going to be jumping around items that are in memory, you should stick to other type of data structures that do that. In generators, once the data is generated and used, it's going to be lost. You don't have the chance to go to the previous element. So that's why I try to do this comparison this way. But that's a great thing to notice, so I will take it into account for updating it as well. So thank you.
Thank you. Anyone else? Anyone wondering about generators, or are happy? You're not happy. There you go. That's good. That's good. We're here to share ideas.
No, it's not a question, but I love the presentation, and I really like that you mentioned the structures and interpretation of computer programs. That's such a good book, and yeah, I think it's even if it's scheme, it's just a good programming language book. So yeah, no, great. No, thank you very much.
Thank you very much. I really appreciate it. Yeah,
Okay. So, Martin, again, here we go. This is getting lively. It's good. We have time. We have time.
Yeah. Very good on time.
Last question. What about any other lazy classes or lazy computations which you can also offer instead of generation? What do you know?
To be honest, I think that generators are the mainly that I've been focused on, or maybe exploit when I have to do something lazy. I think that we can go even deeper into Python, maybe with coroutines, but I haven't dig deeper enough to check that and check how it might help us to do lazy evaluation in that way.
Okay, what about lambdas, for example?
Well, lambda is, well, as far as I understand it in Python, a lambda is kind of a, well, it's like the unknown function, right? So with no declaration. So I'm not sure if that one is lazy itself, but I'll have to double check. Yeah?
Yeah. A function you don't call is lazy, right? You call it whenever you want.
Yeah. So
Okay.
yeah, there we go. We can exploit lambdas as well.
You can build the world, a lazy world with Python and generators. Yeah.
Definitely see you next year with lazy lambdas or something like that.
Sure. Anyone else, or shall we wrap this up? We're wrapping it up. Please, one last round of applause for Sebastian. Thank you, Sebastian.
Great. Thank you very much. So, well, if you have any further questions, feel free to reach out to me on LinkedIn, or if you want to see some of the code that I explained here, you have the slides there. Check the QR code or maybe the URL itself. And before I jump off the scenario, would I ask, is okay if I take a photo with all of you, like holding hands up, just for memories, you know? Great. Thank you very much.
You,
it's been a great
Sebastian.
audience.
Thank you.